Welcome to the Royal Meteorological Society, East Midlands Centre. I'm Mike Stephen, I'm chairman of the East Midlands Centre, and I just want to say a little bit about the Society before introducing the speakers. The Royal Meteorological Society, for those who aren't members, works to strengthen the science of weather and climate and to raise awareness. The local centres, like ourselves, exist to bring the Royal Meteorological Society to its members in the region, and also to help broaden interest in the public, among the public at large. Now, for the seminar, you can ask questions, and we encourage you to do that. You'll find a little box labeled Q&A at the bottom of your screen. If you click on that box, then you come across an area where you can type in your question. And at the end of the session, I'll be going through the questions and asking the speakers to address them. If you have further interest, you want to follow up, you can look at the Society website. There is membership, of course, costs money, but if you have a general interest, there's a free online newsletter called Met Matters, which you can sign up for, which is, as I say, perfectly free. Now, our speaker tonight, in fact, we have two speakers. Dr. Ioana Culfescu is a senior research scientist for the National Centre for Atmospheric Science and also at the University of Oxford in the Department of Physics. She works on computer modeling of climate processes and has been involved in projects in many parts of the world. For this talk, she will be assisted by one of her students, Beatrice Diana, a master's student from the University of Trento in Italy. Now, for those of you who are from the East Midlands, that is not Nottingham Trent University. Trento is a much older institution. She will be giving some points about her own studies of temperature extremes in the Alps. And so now it comes to the time to hand over to Ioana. Thank you very much.
Thank you very much for the introduction, and thank you very much for inviting us. Yeah, so I'm just gonna get into, before I start, I would just want to mention we are also thanking to Professor Dino Zardi from the University of Trento and Professor Massimo Bolasina from the University of Edinburgh for feedback on the presentation, and they are also co-supervising Beatrice in part. Yes, so I'm going to start by going through an overview of the presentation. In principle, as you saw in the title, we are going to talk about how climate change is affecting mountains. But in order to understand that, I'm going to talk a bit about why are mountains important, then how exactly are mountains changing because of climate change. One of the big questions, which is always at the heart of climate change, how can we say the change can be of anthropogenic nature versus other kinds of changes, major impacts, and then Beatrice is going to talk about, is going to present an example of changes in extreme temperatures in the Alps, and then speak about glaciers in the Alps and the recent changes which have been happening in the glaciers in the Alps. So to start speaking about why mountains are important, this is a schematic, an overview of some main points of importance of the mountains. And I hope you can see my pointer here. So first of all, when we speak about mountains, we think about the coverage, the spatial coverage, and mountains cover about 30% of the Earth's surface. And obviously with that coverage, and they are fundamental for agriculture, some of the main crops we are using everywhere in the world come from the mountains, such as potatoes, and the same for livestock. You can see here some Andean llamas. They are very important for agrobiodiversity because in part they are key for a sustainable food system, in part through the biodiversity and preservation of certain species, they can provide more variety in the species that we are losing in the plain. They are very important in terms of climate, in shaping climate, and I'm going to dig into that in a second. Water, they provide most of the world's rivers are originating in mountains. Obviously for us, humans in particular, they are very important for tourists because, and consequently, they also generate income through tourism. And also they are very, very important in terms of biodiversity. So half of the biodiversity hotspots are located in the mountains, and then 30% of the key biodiversity areas are located in the mountains. And as I said in the beginning, we want to explore here how climate change is affecting all these points I raised here. But first of all, a bit more of some particular aspects discussed here. So for example, why are they so important, let's say, for climate? And the first thing, so mountains basically act as a barrier for air masses, and they can shape the climate, not only through being a barrier, but if you look at this schematic here, you see this is an air mass coming from like a windy air mass coming from the water, from a water body hitting a mountain here. And what you can see is that as the air is lifted due to a decrease in atmospheric pressure, there is the moisture evaporates, and you have on this side of the mountain, we have winds, we have rain, we have these clouds forming. So therefore, the vegetation and all these conditions here are wetter, and basically the vegetation is more lush. Whereas on the lee side of the mountain, which is the other notion, so we have the windward side and the leeward side, as the air left the moisture here, as it descends, we have less water vapor, resulting in more dry condition and warmer condition and less vegetation. So mountains are clearly shaping this air coming from the sea, and consequently they are shaping the climate on each side of the mountain. And this is very important because large mountain ranges can have obviously impacts on the climate on a very long range, not as only as this schematic here. And this takes me to a second aspect in terms of the importance of mountains. So mountains provide between 60 and 80% of all the freshwater resources of the planet. And they act as what I call here water towers. First of all, if we go back to the previous slide, this is only a part. You can see so the cloud formation on this side of the mountains. And then I thought it's interesting to mention, so the clouds that you see here are clouds, they are called silvagenitus clouds. And they basically form over forests in general in tropical forest where the vegetation is very lush and there is a lot of heavy rain and condensation because of the forest. And you have this moist laden air currents, which are always deflected up by the mountains. And these forests are very important. This is a picture from Scotland, which shows all this evaporation. It's a forest actually at the side of the sea. And these cloud forests are actually very important for maintaining hydropower performance for major cities in South America, in particular, like Rio de Janeiro, Sao Paulo, and Bogota, because they rely on hydroelectric dams to provide electricity. And also they control basically all this rain here and all the clouds, control and regulate stream flows. And so speaking of South America, this takes me to the third point I want to make, which is basically mountains are very important for food. And here there is an illustration of one of the main crops which needs high altitude and is normally grown at high altitude. This is a farmer in the Andes cultivating potatoes, which is obviously a staple for the South American diet, but not only, it's for all of us. And it's very important. So the areas, the microclimates and the temperature gradient across the mountains it's very important for cultivating different types of potatoes and different varieties. And the second thing I want to show, it's actually the second food, which is a staple, it's actually coffee. So coffee thrives in forested mountains, for example, in Indonesia, which is one of the largest producers, and it's largely due to the unique conditions created by the mountains. And I thought it's interesting to illustrate this because with climate change in the mountains, as I will show later, these zones can change. So what you see here on the right is how does altitude affect the flavor of the coffee. And you see, if we are at 610 meters at a very low altitude, coffee is not even cultivated. And as if we go up with altitude on this axis, so you see 760 meters, we have the varieties of coffee which are more subtle and more mellow. And as we reach at the top, 1,500 meters, you have at very high altitude, very complex acidic varieties. So the mountain, the altitude ranges shape this product, which is coffee, and they do similar things with potatoes and other crops. But just as an example to see the importance of the altitudinal range of a mountain. And the last point I want to make in terms of importance is the importance of the mountains for biodiversity. So here there are a few things. If you look to the plot on the left, so first of all, when we speak about biodiversity, it's not only the species biodiversity, which is the first thing which comes into mind. First of all, we speak about the ecosystems biodiversity. From there, we have the species diversity in the mountains. And then the last type of diversity, so within the species, we have genetic diversity. And the mountains are hotspots for all these kinds of diversity. And this is it's a print screen of a paper, which I found very interesting. You can email me or I can put it online if you are interested to see it. It's about the Humboldt's enigma. And the enigma is about, the question is basically, what causes global patterns of mountain biodiversity? And what happens here is in the mountains, if we would consider the same range as in a plain, we still have a much richer diversity than on a similar size, but on a plain. So the paper says here, with about 25% of land, mountain regions are home to more than 85% of the world species, for example, of amphibians, birds, and mammals. And it's called the Humboldt enigma because starting with the voyage of Humboldt in South America up to the present day, there are still debates about why this is happening. And this is a plot from the paper. And what you want to see here is, so this length, if you look at the length of this line here, represents lowland, and it's 100 multiplied with 10 to the power 6 kilometers squared. And this length here in black and the color represents about a third of this and represents the mountains. And then the authors look at, they say, okay, so let's see how many, if we take mammal species, bird species, and amphibian species, how many are in the mountains represented by the black versus how many are on a plain, and also the darker green represents both. So what you want to see here is how big this black part is for each species versus the lowlands, this one. And you can see for the mammal species, there is a big range where we have both. Still, the mountains, so the length of this line here is quite big in comparison to the lighter green. The same for the bird species. And then if we go to the amphibian species, you can see that the majority of the species are actually located in the mountains. So that's quite remarkable. And again, it has huge implications for climate change in the mountains. So the conclusions from this first part of the talk is that so the mountains are shaping the climate, cloud forest position, and so on. They provide water and food, and they are hotspots for biodiversity of habitat and species. And the next question is now, so we know the importance, how are these mountain systems changing? And I picked 3 parameters in terms of changes. The first of one is temperature. And we all know that because of climate change, temperature is changing. So what I selected here, this is from a paper by Pepin et al. 2022, is the rate of mean warming versus individual studies in the mountains. And here on the x-axis, you have the time. So we start in 1940 and we go to 2010. And on the y-axis, you have the temperature trend, so an increase in temperature in degrees Celsius per century. So if we look at these two curves, the red and the blue, the red represents, let's say, an observational product, and so does the blue. And you can see, if we use observations for mountains, this is an average, up to 1970, we don't see much increase. So temperature is a bit like maybe about 1 degree. But then, again, just only look at the red and blue. Both observational products show that we start having a trend which is an increase of temperature. So what this says is that from 1970 up to 2000, we got about from about 1.5 or 1 to 2 degrees. So 1 degree Celsius, the same or a bit lower for the blue curve. And the black triangles represent now global synthesis studies, which agree. So the question is, do these studies agree or disagree with the increase in the trend? And what we are looking at is, so if we have the black triangles on the upper side, so 2-4 degrees, it means we have an increase. So the global synthesis studies show yes, we do have an increase in temperature. You see here and here, and there is clearly a positive trend, this black curve. And then the colored circles show mountain regions for different continents. You see Africa is in like this green teal, Europe is in orange, and then, for example, the Tibetan plateau has this cream color. And if you see for example, you see the majority of the dots is above the red curve and above the black curve, and seems to be going up. So there is clearly an increase in the temperature in the degree Celsius trend for the Tibetan plateau. Some of these dots actually show huge values. This would be 8 degrees Celsius per century. So that's an enormous value. And then for other regions like North America, or we have maybe smaller values. There are some points here, these are very few. So the majority of these regions and studies are pointing out to the fact that there is clearly an increase in temperature. The second parameter, so temperature is one. The second parameter through which mountains are changing through anthropogenic influence is pollution. And these pictures mostly speak for themselves, but what I wanted to point out is this was an article, I think, in The Guardian, probably last year. So the article says microplastic pollution found near the summit of Everest. And at the same time, the same microplastic pollution was discovered in the Mariana Trench, which is the deepest point on Earth in the ocean. And this picture here shows a lot of rubbish at the top of a mountain. And the main implications here are when, if you think about the fact that there was pollution found at the top of the mountain and in the Mariana Trench, then one can make the link and think, okay, there is all the cycle. For example, if we have the pollution at the top of the mountains through the water cycle and through the streams and through the groundwater, this pollution actually can, sorry, my dog needs to come in, yeah, just sorry, she's scratching the door. So this pollution can actually end up in the rivers, and through the rivers, which originate in mountains, end up in the ocean. So all polluting the top of the mountains makes all this continuous spectrum of pollution down to the oceans. The third point I want to make is about land use change. So the third way in which we are changing the mountains is through land use changes. And here I just pick on one, deforestation. This is a part from an article in Nature Geoscience. You don't have to look at all this title. What I want to point here is just the word deforestation-induced warming. What this title, I will get back to what this study did, but so the main thing is the authors here are showing a spatial pattern of observations of forest loss during 2000 to 2014 on different continents. And here are the colors represent hectares per year. So the very red parts are losses of more than 3,000 hectares per year. And then the weaker colors represent the smaller loss, still is a significant loss. So what you see here is that in these 14 years, every continent and every box is quite red. So there is a significant deforestation in these tropical mountains. And one of the main points of the paper is that with the loss of this forest is still a climatic effect, which is poorly understood. So we still have to learn actually the big implications of this. So we know now the importance. We saw, okay, there are changes, but of course, if in terms of deforestation, we know humans are responsible, there are changes, like, for example, the temperature, which I showed, which can be, we can have the question, how do we know this change can be attributed to anthropogenic forcing? And here I'm going to present very briefly a classical way of attributing changes to anthropogenic forcing. What you see here is the global mean temperature anomaly from 1900s to 2000 in model, in a climate model. And what this plot shows is, so the model was run, so these big simulations, equations of the climate system was run in a sort of what we call a control run, or so we consider there is no anthropogenic forcing, there is only a natural one. And if you look at the blue curve, if we consider there are no anthropogenic influences, you see the blue curve here is going a bit up, and then it keeps on going up to 2000. We don't really see an increased trend. The shaded blue here is uncertainty. And then we say, okay, how about we don't consider only the solar and, let's say, volcanic forcing, which is natural. We consider we have the anthropogenic forcing plus the natural forcing, which is volcano, greenhouse gases, and so on, the external forcing. And this is represented by the red curve. So once we put in this external forcing, the anthropogenic component, you see the red curve, it's going up, up, up. These curves like oscillate together up to this point. And then from the 1970s, the red curve is going up, and it happens to coincide with the observations, whereas the blue curve remains down. So this is a way to assume that, okay, if we had the model with no anthropogenic forcing and we didn't have this increase, and once we put the anthropogenic forcing, we get the increase, then it means the anthropogenic forcing is affecting and it's inducing the climate change and the change in the temperature, as it's clearly going up. And I want to exemplify this with two papers. So first of all, how can we link, for example, glaciers melting to anthropogenically forced temperature increase? This is from a paper by Vargo et al. And what they did here is they considered a part of New Zealand where there are glaciers. These black dots here are various glaciers, and this is called South Island in New Zealand. And what they wanted to see is how much, so the increase in the likelihood of mass loss of the glaciers, for 10 glaciers, because of human-caused climate change, when compared to a scenario where there is no climate change. So they run their model, like, let's say, in this blue regime, and then they run their model in the red regime. So if you look here, we have two parameters. So, and then they considered, okay, if we have the anthropogenic forcing, do we have a loss in the mass of the glaciers, and what happens to the snow line? And this is the separation between the two metrics. And if you look at these two lines, so if you look at the bottom here, 0 represents the scenario in which we would have no changes due to anthropogenic forcing, and the colors are two different here. So the orange is this glacier Brewster for 2018, and the blue is the same glacier for 2011. And you see this measure here, in both years, so went up 40 times in 2011 and 80 times in 2018. So what this says is that the likelihood of a mass loss for this Brewster glacier is 40 times more likely and 80 times more likely in each of these years respectively because of anthropogenic forcing. Similarly, for this other glacier, they saw a smaller likelihood, but it's still an enormous number. It's 30 times more likely, and then something like 13 or 14 more likely for 2011. And then for the other parameter, for the snow line, so you see all these glaciers, all these bars here are positive. So on average, it's something like 10 times more likely to have a snow line loss for each of these glaciers in both years. So there is no line that goes downward here. So it's clear that anthropogenic forcing, which was so done in the run they considered, is increasing the likelihood of loss in the ice extremely for all these glaciers they studied. And the second example, going back to the paper I showed you before, it's about the temperature change through deforestation. And what this study did, it's Zheng et al. 2020. So the authors they focused on these boxes in 4 continents. So a box in South America, one in Africa, the maritime continent, 2 of them. And they said, okay, we have a deforested land here. How about we consider, they took a mathematical model, a climate model, and they considered they didn't have the reforestation in these boxes versus the scenario in which the deforestation happened. And here they plotted, so where you see the red color represents what happened, the difference between the deforestation run and the forested run. And what you see here is the increase in temperature. The red colors are an increase in the case of the deforestation. And you see the order here doesn't correspond exactly to the boxes, but the main point to take is like this one corresponds to the maritime continent, and probably this is Africa and so on. But the main point here is that where you have the red color, actually you have an increase in temperature, and the increase in temperature, so here is about 1.8, and it's quite a big area. There is hardly any decrease. There is a bit, but there is hardly anything. So due to deforestation, we clearly have the increase in temperature. This is really red and orange almost through all this part. The same for the third box, so it's red and orange, and the same for the fourth box. So this is another example of a modeling study where we can attribute climate change to anthropogenic forcing. So the conclusion here is that while models do have imperfections, and there are still many issues, especially at local scales, which need to be answered, the overall agreement is that the trends can be attributed to anthropogenic forcing. And I'm gonna dig a bit into some of the major impacts before I leave Beatrice to speak about the glaciers. This is a schematic of some of the major impacts of climate change in the mountains. And probably this schematic in itself would take like half an hour or to discuss, or much more. But the main thing here is that the clusters in which this schematic is divided contains some of the main problems. So there is a lot of uncertainty of precipitation, which comes from climate changes in the mountains. First of all, you can imagine, as I said before, because of the mountains representing barriers or producing precipitation, we don't know with the change in the temperature gradient what will happen. Then we have one of the main problems, and we are going to touch a lot on this, is the ice reserves are decreasing. No reliable water sources, especially in the summer. That was a problem I'm going to give an example about for France. Then at the bottom of the mountains, there are ecological changes, and then throughout the entire height by elevation and season. And then really low, we have all these changes. Of course, if you think, you know, the water coming from here, the water availability, decreased water availability in drylands and lowlands, shift in the water supplies, and last thing, it's there are problems, especially in terms of slope stability or increased risk for flood outbursts for example, for glacial lakes, which I'm gonna touch on in a minute. So some of the major impacts I'm gonna illustrate are, so first of all, this is, since I spoke about coffee before, first of all, this presents, this is an example of how the deforestation and climate change might affect coffee in Indonesia, because they have less rainfall and drier conditions. And you can see here, so this is 1996, and as we go further in time, 2016, the Y represents the number of boxes of coffee. And these are key variables linked to climate change. So hurricanes are in blue, drought is in yellow, and then the market, it's pink, it's a bit here and a bit here, and then pests and diseases. And you can see that wherever we have the hurricanes and the drought, which are linked directly to climate change, we see like huge oscillation in these coffee boxes. And while we have a decrease here because of global economic recession, basically the decrease between this point here and the point here where there are lots of droughts, then it's quite significant. So this is one example. The second example of major impacts is linked to the water cycle, which I presented before. And this is an example of the Rhone Glacier in France. This is a picture from 1900s, and this is a picture from 2008. You see the clearly decreased size. And a direct impact happened this summer. So in summer, France, which gets about 75% of its electricity for nuclear power plants from the Rhone River, was affected by the fact that actually, because this glacier didn't have enough ice and the water got too hot, they actually had to shut down the power plant. So there was directly the link between the depletion of the glacier, less water, warmer water, and the electricity production in France. Another thing which I want to point out as a major impact or as a major source of uncertainty is when we think about the vertical distribution. So the main thing which I mentioned before about biodiversity is that on a mountain we have, on a very small area, if you think here on the vertical, so this is 0 to 8,000 meters, so from 0 to 5,000 we have about 1, 2, 3, 4, 5, 6 different microclimates, alpine zones with different biologies, different systems. So we have a huge diversity. And now the question is, if, assuming this is the current climate, so you see this is the temperature, the color represents the temperature, this is warmer, as you go up, this gets colder. And assuming we have, this represents a type of animal or a plant or a system, and there is a link between these two, and this is the habitat for the first one, and the second one has, let's say, this range of habitat on the vertical, so it would be between two elevation zones. In the scenario of climate system, what can happen? So assuming the habitat, this bar here, will somehow translate to, so see the color is changing, so the temperature increases on the vertical. The question is, if we increase the temperature here, what will happen to this bar? So one scenario is the habitat will expand, as I'm going to illustrate in the next slide. Another scenario is the habitat will shift. And another scenario is the habitat for this particular one, for the one on the left, will shrink. And some of the main uncertainties are over the question, if we consider this relationship, if you think the habitat for one of them, let's say, will expand and for the other one will shrink, of course, some connections will be lost. This can bring extinction and so on and so forth. And this is very, very hard to evaluate in terms of the multitude of species and their relationships. And on this line here are two examples of such a situation. This is a paper speaking about riding the elevator to extinction, and it's an example of some direct threat to Scotland's Arctic alpine plants. This is the plan. And what this paper says, it's what they did is they analyzed this type of mountain plant from Scotland since the mid-1900s, and they found out that the Arctic alpine plants decreased by over 50% and the lower elevation plants expanded. So these are disappearing and they are replaced with other plants with more competitive neighbors taking over. The second example is about butterflies in the Alps. The conclusion of the study is that climate change drives mountain butterflies towards the summits. And this is clearly illustrated in this plot. So this is the plot, this is a picture of the richness of butterfly species in 1965, somewhere in the Alps. And where you see red here, you have a high richness of species. Now, if you look at this plot and you see there is a lot of red, and we go to 2015, the red clearly decreased. You see it's a bit here and a bit here. And here you can't see the elevation, right? You just see the longitude and the latitude. So the question that the study addressed was not only did the butterfly species richness decrease, was also what happened regarding elevation. Did they go higher? Did they go lower? And this second plot shows, so this is for 1965. On the x-axis, you have the density of species. So the more you go to the right, the more species you have. And then on the y-axis, you have the elevation. And you see here at about 2000 meters, we go a lot to the right. So you can see this peak at 2000 meters is the highest. So this means that the species, the most richness of the species was about 2000 meters. Now, if we go to 2015, the same thinking, if you look at 2000, if we would draw a line here, we're actually not, the main density is not centered around 2000, it's a bit higher. And then we have another peak at about 2500. So the species actually went up towards the summits. And the last two examples that I have, so other major impacts are regarding ski resorts. It's not much to say here. This picture speaks for itself. This is the highest ski resort in the world. It's at 5,395 meters. And this is in 1984. You can see how it was covered with snow, and then there is basically nothing anymore in there. There are similar problems in Scotland, where the snow cover is lost at an alarming rate. This is a picture from a paper saying that by 2080, all this area, like in the Cairngorms, and will be snow-free. This is a picture of the remaining, what is called the Scotland's glacier. And this glacier has melted away 2 years consecutively for the first time in the 1800s. And this is another picture from a glacier in Svalbard, illustrating the fact that, see, 1900s, the extent as well as the thickness were clear. And then if you look now, it's nothing. And the last impact before Beatrice will take over is regarding what this melting poses as threat to life. If you look at this satellite picture here, you see at the tongue of these glaciers, which are melting, there are some lakes. So this glacial lake outburst, so you have one here, one here, one here on the other side. So this glacial lake outbursts are producing a lot of damage in terms of sediments, glacial debris, as well as, for example, in Peru, which experience some of the most destructive glacial outbreaks. There are people who are killed. So in this case, 3 such floods killed about 6,000 people. So it's really, really, really life-threatening. And on the same line, the same things happen with avalanches or increased logfalls. For example, the accident in 2014 on the Everest, 16 climbers dead. And a fact on the side of this is that Everest is on track for a glacial loss of about 70% by 2100. And to speak a bit more about what this means in terms of threats and life loss and damages, Beatrice will give examples of changes in the extreme temperatures in the Alps.
Okay, let's start now with some examples. I will speak about 3 glaciers in Italy. I'd like to start with this video, which is showing the Microclimates glacier Okay, this video is showing the Marmolada Glacier at the beginning of July 2022. The 3rd of July of 2022, so this summer, a piece of the Marmolada Glacier melted off and fell off the mountain. So more precisely in the Alps, you can see the position of the Marmolada Glacier in the upper right of the slide. It is at an altitude of about 3,300 meters. This important unplanned glacier started its retreat decades ago due to climate change and due to global warming. And see how strong and fast the ice is falling down the mountain in this video. And see how the ice is almost all melted and there are almost no white region left. So this huge disaster killed 11 people in total and a dozen are wounded. So I previously announced, here I would like to present you the Marmolada Glacier in 1920 against 2009. During this 90 years, the ice melted due to the increasing temperature caused by climate change and global warming. So the slow melting of the ice caused the disaster I showed you before. See the red circle, how it decreases in size. In this picture, it is possible to see again the situation of the Marmolada before climate change is 2010 and after, so last year, 2021. The decrease in the coverage of the ice is clear. Before it was reaching this position and now it is over there. But let me show you more precisely the situation of the glacier before the disaster in the left side and right after the detachment of the ice. The small black arrows are showing the direction of the mud and the ice, the melted ice, falling down the mountain. But in order to better understand, let's see the size of the hole that left the detachment of the ice. See it compare with an helicopter. So, and imagine how much ice fell off. Another important glacier that is suffering because of climate change and increasing temperature is the Presena Glacier. Its retreat is clearly visible in this picture, and see how the snow and the ice is decreased in this region, before and after. In order to preserve and slow down the ice melting, the use of geotextile fabrics, here, I want to show you the video. This use of this geotextile fabric in the Presena Glacier is taking place. Since 2008, every summer, the glacier is covered using this smart fabric in order to protect the ice from the solar rays. Many glaciers are suffering, and many of them could disappear in 50 or 20 years. During the last decades, in more than 200 glaciers have disappeared. The melting can be slowed down using this geotextile fabric, but their fate is inevitable, since its use is quite useful, but not sufficient. The Presena Glacier is now turning pink. See these pictures. This is nice, isn't it? Well, this is not what it seems. The red shades are given by a recently discovered alga in the Alps that dyes the snow, but also accelerate the melting of the ice. This alga absorbs the solar radiation and increases the temperature of the ice and the snow, causing the snow melting to accelerate. Scientists are still studying this new alga that is making the situation worse. The third and the last disappearing glacier that I'd like to present to you is the Adamello one. See its retreats from the picture and how much snow melted during the last 100 years. Talking about the Adamello Glacier, let me show you this video. This video is showing the Adamello Glacier melting this summer. So the water that you see falling down is the melted ice and snow. Please focus on the motion and the speed of the water, and all of this were ice. And as you see the helicopter that is going upward, here there should be ice, instead it's basically all water. So due to the drought condition Italy experienced this summer, Alpine guides refused to work and to accompany people in Mont Blanc and Monte Rosa because of the high probability of dangerous event in the Alps due to the glaciers melting. So there should be more damages, and the damages related to this latest disaster can be listed as follows. So there could be economic damages, for example, due to the expensive cost of geotextile fabrics used to cover the Presena glacier, which amounts is about 420,000 euros. Moreover, as the glaciers are melting, fish are changing the natural behavior and are laying their eggs in different places, leading to problems and damages to the fishing economy. To continue, the ice melting is releasing in the water new microbes never seen before, living inside the glaciers that can be responsible for new pandemics. To conclude, damages related to tourism must be accounted as well, due to the fact that the Alpine guides refuse to stop the visit in multiple mountain sites, and tourists might be afraid of disaster and danger in the Alps. So because these damages are directly related to the human influence, global warming, and climate change, as part of my latest computation, I'd like to show you some more graphs about the heat waves. But first, let me tell you what's a heat wave. The heat wave, or also called hot spell, is a prolonged period of time, usually for more than 5 days, characterized by air temperature values above a certain threshold. My result is presented here. As you can see from this plot, in the x horizontal axis, we have the percentage of the size of the area that is affected by the heat wave. And in the y vertical axis, we have how many heat waves occurred. I wanted to show you this to point out the different impact that global warming and climate change might have on different regions. You can see here the seasonal, so each panel in this plot is a season. Panel A to represent the winter, panel B the spring, and panel C summer. Panel D, autumn is not present because it was very similar to panel B, spring. You can see here the heat wave occurrence in the plain, in the green and the pink curves, and in Alpine region, in the blue and in the orange curve. It is possible to notice that each region is split into two periods as follows, so 1951-1980 versus 1981-2021. It is clear that for each season, the life for the second period, 1981-2021, goes always above the previous period, 1951-1980. So meaning that the heat wave occurrence is increasing in both plain and Alpine region, caused by climate change and global warming. If we want to focus in this plot, starting from the winter until summer, we can notice that the blue Alps is always, blue Alps 1951-1980 curves is always above the line 1981-2020 Alpine orange curve. Meaning that especially in the Alpine region, the heat wave occurrence has decreased after 1980. Moreover, this plot is really useful in order to understand that for the Alpine region is suffering more than the plain, and this may lead to disaster and accident like the one that happened in the Marmolada this summer, because it is possible to see that the Alpine curves as always above the plain one, meaning of course more heat wave with respect to the plain. So to summarize, mountains are changing through increased temperature, pollution, and land changes, for example. Changes can be attributed, of course, to anthropogenic factors. Some of the major impacts include melting glaciers, loss of biodiversity, water sources disruption. And temperature events and overall increase in temperature can contribute to the change, for example, ice melting. But despite this predicted hill effect on our coffee supply, all is not lost. There is a lot of work to improve agricultural practices and protect forests, especially in the mountains, to make ecosystem more resilient. We need to promote more sustainable tourism in mountain regions to prevent health and reverse the degradation. Thank you. If you have any questions, they are welcome.
Hello. Thank you very much for your talk. I don't see any questions there, but I have a couple myself. After your comments about the effects of mountain climate on coffee, it's a shame that we can't have coffee together and maybe do a tasting of the different types. My question, many years ago, I worked in Nepal as a climatologist, and one of the unusual aspects of glaciers in the Himalayas is that the accumulation season for the glacier and the ablation season is actually the same. It all occurs during the summer monsoon. In winter, it's cold and dry and nothing happens. So they're very sensitive to the immediate local conditions. I'm just wondering whether that sensitivity, if there's evidence how that sensitivity has translated in or has affected their response to changing climate. Do you know what evidence we have of that?
I think, well, we would probably need an expert in the monsoon, and I'm not one. I was just, so first of all, I'm sure this, like the increased sensitivity and the interrelationship between, yes, the mountain and the monsoon is definitely a factor which can affect this, especially through disruptions in the seasonal cycle or the onset of the monsoon or the different amounts of precipitation or so. Yes, and I was trying to look here. I don't have any study in mind to point out to, but I was trying to look here at the, so for example, at the Tibetan plateau, like we clearly can see from the studies, yeah, it's, I mean, here, the cream points are clearly above the rest. So I would say since that area is, obviously the interrelationship between the monsoon and everything else is the main factor determining the climate. I think yes, absolutely. But at the same time, I think there are studies linking glaciers. I know about Europe, I'm not sure about Asia, but with, for example, the Arctic melt or the circulation. So there is probably an interplay between remote factors and the local factors such as the monsoon. That would be my answer on that.
Thank you. I have a question from Cheng Wan Wei. Thank you so much for your talk. Very impressive and informative. I wonder how the speakers think about the hypothesis of elevation-dependent warming or elevation-dependent climate change.
So that's, yeah, thank you. I'm not gonna, I clicked on the question and I don't know how answer live. Okay, I can't, okay, I couldn't move the window. Here it is. Yes, I think that's a very interesting question, and actually linked to that, I can point out to this paper. So you see, this paper actually speaking about the elevation-linked warming. So this paper actually says the deforestation-induced warming is regulated by elevation. So I think depending on the study and depending on the region and depending on the hypothesis, the elevation can regulate or somehow counterbalance or make it worse. So does that answer your question?
Thank you very much for that. I have another question on the, I was intrigued by the reflective fabric being used on the glaciers in the Italian study, Beatrice. How effective is this treatment for the glacier? And has anyone done a cost-benefit analysis of that? It seems a very strange thing to do, to cover a glacier with a piece of cloth.
Can you please repeat the question? Sorry.
Sorry. Yes, you showed some slides of people putting reflective fabric on the glacier in Italy, in the Alps, Italian Alps. I was wondering how effective that was at reducing melting, and whether anyone had done a cost-benefit study to see whether it was worth the money, because it was an extraordinary amount of money you were quoting there.
Yeah. Actually, this is not sufficient, and the ice is melting, even if there is this smart fabric that is covering the ice. The money comes from the Italian government, and yeah. So actually, they are investing a lot of money, but this is not actually useful because the ice is still melting.
Okay, thank you. Okay, I have 3 more questions here. Nick Pepin, thank you for your talk, wonderful talk. Do you think mountain precipitation will change in a different way to lowland precipitation? Will there be elevation-dependent precipitation change?
So Beatrice, who is looking at the changes in mountains versus lowlands, didn't look at that before, but I think that's a good idea. We could look at it, because we wouldn't be able to answer that, but that's a good point, because she only looked at precipitation, so we can't say that. But I mean, I imagine, given what we showed, right, that mountains are really linked to precipitation, and probably since we have, especially in the tropical areas where we have the forest clouds, definitely if those change, then the water supply and the precipitation, everything in the lowland will change too. So I would say they are quite linked, but would be interesting to, this is just speculation, would be interesting to look into that.
I have a question asking about, is there evidence of change in the start of the Asian monsoon? This is perhaps not your area, I don't know.
I know, no, I wouldn't be able to say what the link between mountain climate change and the start of the monsoon would be. But again, I would imagine with a different, like with different precipitation and linked to the mountains as a barrier, the monsoon will change differently. But at the same time, the monsoon is linked to the sea surface temperature. So I wouldn't know. I can't make a statement on that. Yeah.
I think I can say from my time in that part of the world that the dates of the monsoon are notoriously variable, even in times when nothing else is changing. So it would be very difficult to see any effect specifically related to mountains. It's a very variable thing, variable by several weeks sometimes.
Yeah, so who knows if it's linked to mountains directly or the sister. Yeah, so yeah.
Question from South Derbyshire CLP. Can we quantify effects between general warming, a change of tree cover at lower levels, and pollutant changing surface albedo? So this is asking, can you differentiate the different causes of the effects on mountains?
There are, so obviously models are used for that. There are currently large ensembles of models run, like there is something like there is the CMIP, it's called LUMIP. So basically these simulations are done with different types of land cover, like deforested area or crops or on and off. And those are tools and produce data which we can analyze and then quantify these changes. Obviously, there are uncertainties and it's very hard to compare them with the reality because you need clear long-term observations of this cover, and we don't have like I don't know, hundreds and hundreds of years. So while the models can give us a clear insight, there is still uncertainty, but I would say yes, quite to a good degree with the models.
Okay, thank you. There's 2 more questions here. Following the earlier question, this is from Mike Longman. Following earlier question, do your studies show that some mountain species will be trapped to the location due to climate change, i.e. not able to adapt to either the thinner atmosphere or temperature changes? So are species at risk because of the changes?
That's a very tough question because we are not experts in biodiversity, but I imagine I don't know if so much trapped, but one of the main problems with climate change happening so fast is that species don't have enough time to adapt. And we all know the example of the polar bear. So I imagine in the mountains is the same issue, like with the changes coming so fast, or especially stress factors such as heat waves or very sudden, really shocking perturbations. Yes, I'm sure there will be species, and we know it's part of the extinction problem that will not adapt in time, either through no time to migrate or to find new habitats, or simply for running out of the main food supply. So yeah.
Okay. The final question is from a skier, Lorna Ogilvie. There are ski resorts where covering the ice with a blanket has been done to protect the link from the lift system to the ski runs. So this is like your the thing in the glacier in the Alps. I'm a skier who worries about the future of my sport, not simply selfishly, but for the local economy. How do we get the message about climate change out there more strongly? It's more a political question rather than a skiing question.
Yeah, exactly. I mean, that would probably need an entire meeting and addressing that question in itself, right? Because getting the message out there from the level of, let's say, local communities up to the government is one of the main challenges we are facing. So I'm not able to say that. I'm not really into I guess you need, how do we get the message? I think the scientists and the comms teams and like scientific organizations working more closely with local organization, which you know, it runs down to more time, more money. I don't know. I wish I would have the answer. It's a very complicated issue. I think in general we are all quite aware of the impacts of climate change. So maybe at this point I would assume there's quite a bit of awareness. So maybe the message is there, and we have to think more about mitigation and adaptation. And then, as you asked initially, is this an effective way to tackle the problem, like covering the glaciers? As you asked, there are tons of money going in, but then if the glacier melts from below, what's the point? So
I think actually your talk is a very good example of how to get the message out, because you've given many examples of effects on real people and or real activities in different places, whereas a lot of the climate discussion is very abstract. You've made it very specific, so I think that's perhaps the way to do it.
Oh, we are happy to hear that. Yeah, that was that the message came. Yeah, because even I learned, like we learn things, and like the coffee distribution, or that was quite interesting. And it's really a direct impact. And
you start talking about coffee, it's serious.
Yeah.
Well, can I wind up now by saying thank you, first of all, to attendees, for all the people for attending and for all your questions. Secondly, a big thank you to both our speakers for giving their time and their expertise and for answering the questions so effectively. A couple of just follow-up points. There should be a round of applause at this point, but unfortunately no one can hear us. Talks will be available to see again on video if you click on the event page on the Royal Meteorological Society website. That's the same place you had to go to register. But it will take a few days, so don't look tomorrow, look in maybe a week's time. And if you want to follow up interest in the Society, if you're not already a member, again, look at the webpage. And in particular, if you want to get on my mailing list for the local group, email the society and things will trickle down and I will sign you up. So thank you very much once again to both our speakers. And
thank you too for inviting us.
And to the audience for participating, and have a very good evening. Thank you.
Thank you. Bye.
Bye-bye.